Okay. Okay, let's go ahead and get started. I am going to shut the door so that there's no extraneous noise. I have a voice, but it's not as strong as normal, so I don't want to be too loud.
Did you get that record for a second?
Yes,
Oh,
I'm
you're
also
recording. Never
recording.
mind. Sorry, I forgot that you did that.
Yeah, I try to be, I'll try to record everything, so. Okay. The way this is going to go, so just to give you a little bit of an idea of how the rest of the week's gonna go, I'm missing yesterday and not 100% today. Number one, I am going to discuss integrated rate laws. It's probably going to take me a little longer than normal simply because I'm not 100%. But we're going to deal with integrated rate laws today. Tomorrow in class, we'll talk about collision theory and the energy of activation diagrams and stuff of that nature. And then on Friday, Dr. Yang will be with you and he's going to discuss reaction mechanisms. As far as your exams are concerned, I'm on page 7 of 9 in grading them. So my goal is I'll try to get them done by tomorrow. It's partially going to be dependent upon how things go the rest of today and in the morning. But I'm going to try to get them done and get them back to you. I should have the grades posted minimum by the end of the week. And at minimum, you'll have your test back on Monday. I normally try to have exams back within 1 week of giving an exam, but I kind of got delayed a little bit. So, but I'll still try to get it back within a relatively reasonable amount of time. Speaking of the exam, I know it was long. And if you knew what you were doing, it was doable, but I know it was long. But other than long, was there anything on it that wasn't expected?
I think there was something that was like miswritten. I don't know if anyone brought that up to you, but it was giving like the molar mass of something and it was the exact same.
Somebody did, and I put the change up on the board.
Oh, I just was not.
Yeah.
That's me.
I was wondering what you're talking about.
No, I'm still sorry.
Yeah. That's sometimes happens when
Yeah, I
I'm
just-
copying and pasting, cutting and moving and yes. I mean, I did the numbers were correct. It just had the wrong formula for one of them on the last problem or next last problem. Other questions, comments? Okay, because I won't promise that. I never make a promise that the exams aren't thorough, but I do make a promise that there shouldn't be anything on there that's not expected. That's one of the few things I can definitely offer, is that it should be expected, and if you do the optional homework, there shouldn't be any major surprises in how things are written. So, any questions? Okay, so last week we started discussing reaction rates, and come on, give me my. We said that we could describe the rate of a reaction as being equal to the disappearance of the change in concentration of the reactants over a change in time. Goodness gracious, I hate when it does this to me. Drives me up a wall. And we represent that as a negative value to represent that the concentration is disappearing. Or you can describe the rate of the reaction as the formation of a change in product over a change in time. Basically, looking at this formula, rate is speed. It's the speed of the reaction. I mean, just like when you talk about the rate at which you're traveling down the road, you describe it in how many, the change in the number of miles you go per hour, the change in time. You're doing the same thing here. You're describing the change in, it's just, we're talking the change in concentration of either the reactant or the product versus a change in time. So we're talking about the speed of the reaction. And we worked a few problems dealing with the rate. Then on Monday, we started talking about rate laws. Rate laws are always written in the same format. There, the rate is equal to the rate constant times the reactant 1 raised to its order times reactant 2 raised to its order. And we could continue for however many reactants it is. And what we started our discussion on Wednesday of last week is that these orders, the X and the A in this particular case, can be determined only by experimentation. And there's a couple of different methods that we can do this. We can do it using the method of initial rates, which is what we did on Wednesday of last week, or we can do it using the integrated rate method. And today we are going to talk about integrated rate laws. Again, the integrated rate law is going to allow us to determine quite a bit of information. It's going to allow us to determine the order with respect to a reactant. It is going to allow us to determine the rate constant for the reaction. It'll allow us to determine the concentration at at any given time during a reaction. There's a lot of information that can be gleaned from the integrated rate laws. To get the integrated rate laws, as I'm going to illustrate later, we start by collecting data. We collect the concentration of our reactant as a function of a particular time. So for example, we would collect the time, say at 0 seconds, we had a concentration of reactant A of 10 molar. And then we would collect 10 seconds later, and we would find that that concentration of A has changed to 7.94 molar. And then maybe at 20 seconds, that concentration is now at 6.30 molar. And we would collect this data. In the lab, specifically, we will be collecting time and we will be collecting concentration, but we will determine our concentration it's going to be related to the absorbance of our blue dye. So we're going to actually be able to relate the concentration versus time. Once we collect all this data, then we develop some graphs. And depending upon what the graph shows us, tells us all the information I was alluding to earlier, which includes the order with respect to that chemical. It includes the rate constant. It includes the initial concentration. It includes the time at which half of the concentration is gone. So there's a lot of information that can be obtained once you do the integrated rate laws. So we've collected all this data and then we graph. And we create 3 graphs. The first graph is going to be concentration versus time. If the concentration versus time gives the best R squared value, then the order with respect to A is 0. So what that would mean is we would be able to write a rate law that rate is equal to K times A to the 0 order. Now, if you have that rate is equal to A times 0 to the 0, let's think about what that means with respect to how the concentration of our substance impacts the speed of the reaction. Because again, what is rate? Rate is speed. So how does the concentration impact speed? Well, let's say that our A concentration, if I can get this to stop moving, is 1 molar. Well, that means that the rate law is rate is equal to K times the 1 molar raised to the 0 power. Now, what is anything raised to the 0 power? 1. So in other words, this simplifies to rate is equal to K. Let's say A is 2 molar. Then our rate is equal to K times 2 to the 0 power. What is anything raised to the 0 power, 1. So again, that means the rate is equal to K. So if we say something is a 0th order, in reactant A, what it means is that the concentration of A has no impact on the speed of the reaction. And we just proved it mathematically. Now, I said there were 3 graphs. That was just one of them. The second graph that we would graph is we would graph the natural log of A versus time. If the natural log of A versus time gives the best R squared, then the reaction is first order with respect to A. So we can write a rate law that rate is equal to K times A to the 1. Now, we can play the same game that we just played with 0th order. Let's say our concentration of A is 1 molar. That means that this is K, or excuse me, that the rate is equal to K times 1 to the first power. What is anything raised to the first power? Itself. So in other words, the rate is equal to K in this case. We can say, okay, well, if A is 2 molar, then the rate is equal to K times 2 to the 1, which simplifies to rate is equal to 2K. So basically, the speed
Something always.
I have no clue. Is impacted by the concentration. If you double the concentration, you double the speed. If you quadruple the concentration, you quadruple the speed. So it's directly impacted. That's what we mean when we say something is a first order. The third graph that we perform is we will graph 1 over A versus time. And when you graph 1 over A, versus time, and that gives the best R squared. Then the reaction is second order. NA. So in other words, we can write the rate law. Rate is equal to K times A squared. And just like before, we have the, we can keep our thought process. So if A is 1 molar, then the rate is equal to K times 1 squared. Or in other words, it's equal to K. But if A is 2 molar, then the rate is equal to K times 2 squared. Or in other words, our rate is equal to 4K. So doubling the concentration causes a quadruple in the speed. So all of this started with us graphing. And when we graph, every single time, we have looked for us to obtain the best straight line. If we want the best straight line, then we're looking at an equation of y equals mx plus b. Now, we can apply that to integrated rate laws. In the flipped classroom PowerPoints, I actually integrated the integrated rate laws for first order, second order, and 0th order. But I'm just going to get down to the nuts and bolts and get to the table for this first, second, and 0th order. And so this table is going to be something that you're going to reference. And I don't really need it, but I want it. This table is going to be something that you're going to reference, so you may want it on a separate sheet of paper. I can't promise.
That's right. Each time.
Yes,
Once for one.
no,
And then 5 for each of these.
yes. Okay, so the graph. Again, this is going to start with the graph. We're always gonna, I mean, that's the easiest way, is you're gonna start with a graph. Now, for lab, you're gonna be expected to graph. For homework, you'll be expected to graph. For a test, I will give you the graphs. And you just have to be prepared to interpret. But it all starts with a graph. If it is A versus T, you'll get your line. And that integrated rate law that is related to that line or that can be derived from that line is that the concentration of A at any given time is equal to a negative K times time plus the natural log of A initial concentration. And I will give, once I've gone through and written out all of this, I will go in and define all of the pieces because they're the same for every equation as far as what the actual symbols represent. The units of the rate constant is going to be molar per second. And the half-life is going to be T1/2 is equal to A naught over 2K. Again, this is representing a 0th order. Now, if you graph the natural log of A versus time, and if that gives you a straight line, then it is first order. And the y equals mx plus b, the integrated rate law, is the natural log of A at any given time is equal to a negative kt plus the natural log of A initial concentration. The units of the rate constant are simply per second. And the half-life for a first order process is the half-life is equal to 0.693 divided by K. Our third option of a graph was 1 over A versus time. If that gave you a straight line, then it was considered to be second order in A. The y equals mx plus b is 1 over A at a given time is equal to a positive kt plus 1 over the original concentration. The rate constant for a second order is per molar second. And the T1/2 is calculated as 1/K times A naught. In all of these cases, A sub T means the concentration at a given time. K is, as per normal, your rate constant. T is time. And make sure your units match. And then A sub naught is your original concentration. Okay. Now to answer a common question, and that's, are you going to give us this table? The answer is not exactly, and yes. I don't give you the table. I do give you the formulas for the integrated rate laws. And I do give you formulas for the half-life, but I don't specify if they're zero order, first order, or second order. So you need to be able to recognize them. But folks, I give you the graphs. And the graphs are going to tell you which one you need to use. Look at this first graph. It was concentration of A. Just regular old everyday concentration of A. Versus, well, in the integrated rate law, it's regular old concentration. Oh, nobody caught that, and I just now caught that. There wasn't supposed to be a natural law there. The other thing is note that the concentration is essentially in the numerator. It's in the numerator and its half-life. Compare that with second order. First of all, the concentrations in the denominator, and even in the half-life, the concentrations in the denominator. So it'll help you to know, oh, this one goes with this one because both of them, all of them have the concentration in the denominator. That's how you can recognize which one you're working with. And then natural log is an oddball. Well, so is its half-life equation. It doesn't have concentration involved.
Where does that number come from in the natural log calculation?
It comes from the integration that is necessary in order to take the numerical values and get it into a straight line. So we had to do some mathematical calculations in order to convert this original data. In order to get a linear line, you have to do some mathematical integrations to get there. And that's where it came from, is doing those mathematical calculations to get there in the first place. Because we like linear lines. Okay. Now, some key things I want to note. Is these equations have a form. They are y equals mx plus b. So when you are getting the line, the equation for the line, if it's zero order, your slope is equal to a negative k. In other words, your rate constant is equal to the negative of the slope. The same is true for our first order. It's y equals mx plus b. So the slope of the line is equal to a negative rate constant. Or in other words, your rate constant is equal to the negative of the slope. But when you look at your second order reaction, it still has the formula y equals mx plus b, but now your slope is equal to a positive rate constant. In other words, you may have wondered how we can figure out those rate constants. How do we figure out a constant? Well, we do some experimentation. We take the integrated rate law, we get our linear function, and from that you can calculate your rate constant. The other thing you will note is that your y-intercept in the first equation is equal to the original concentration. For our second one, the y-intercept is equal to the natural log of the original concentration. So we have a way, if we don't know our original concentration, to calculate the original concentration. We can deal with the y-intercept. And for the last one, the y-intercept is equal to 1 over the original concentration. So just to back up, number one, got a set of data of concentration versus time. You graph it. You do 3 graphs. You graph one where you graph the concentration versus time directly. You graph it where you graph the natural log of concentration versus time. And you graph the one over the concentration versus time. Whichever one gives you the best R squared, that is your y equals mx plus b. Whichever one gives you the best R squared is telling you the order with respect to that particular substance. Once you have that knowledge, you have the opportunity to do a variety of calculations, to write a variety of pieces of information up. There's a lot that can be gleaned once you do the graph. But you got to get to the graph. As I said, on the homework, on the homework and in the lab, you'll be doing your own graphing. Next week's lab is going to have 6 graphs because you're going to have to graph, you're going to use, I can't remember the exact concentration of bleach versus blue dye. And we are going to determine the blue dye concentration, the blue dye order using integrated rate laws. Because the concentration of the blue dye is going to steadily decrease over time. And you're going to figure out using your graphs which order it is with respect to blue dye. Then you're going to use the method of initial rates to figure out which order it is with respect to bleach. Ultimately, being able to write your rate law. You'll be able to figure out rate constants. I can't remember if it asks you to, but you will be able to. Because it's all sitting here in the information. Okay. All I've done right now is give you details. I want to take a 10-minute break and then we're going to come back and we're going to actually work with this information and do some integrated rate laws. And after that'll take about 30 minutes to an hour and then we'll call it quits for the day. So I'm going to give you a 10-minute break. It also gives my voice a minute to rest. I expect to, as it's now 3:20, I expect to be done by 4:15. Okay. Thank you. Some of these. Oh, okay.
Yeah, usually different for the days.
Sometimes, there's just like it's where usually it's together, but if there's not one, it's not gonna be not together. Like we will only have one, yeah. We'll only have it with.
Okay, let's go ahead and get back into this. What we're going to do now is we're going to look at how you use the integrated rate laws. To number one, how we're going to use the graphing to determine the order. We'll look at how we're going to use the integrated rate laws to determine the rate constant, the half-life, and a variety of other pieces of information, because basically once you get the graph, it is your starting point for everything. So, okay. So what you see on the screen is you have some data. Basically what happened is this person ran an experiment with some compound. And at 0 seconds, they had 10 molar of that compound. After 10 seconds, it was down to 7.94. After 20 seconds, it was down to 6.3 molar, and so on and so forth. And they collected the data for 60 seconds. Then what I have in this column, so this column is just A. It's just the concentration of whatever the substance was. Into the next column, I went ahead and took the natural log of the concentration. And into the final column, I took 1 over the concentration. I then created 3 graphs. The first graph is going to be just the concentration versus time. And when I add a trend line to that and display my R squared and my equation, I get an R squared value of 0.9624. For my second, again, that particular graph is just concentration versus time. In the second graph, it was the natural log of concentration versus time. And when I add a trend line on that one, I get an R squared of 1. Finally, the third one, just because I need to make sure that I know what the order is, I graphed 1 over the concentration versus time. And when I add a trend line to that one, I get an R squared of 0.9623. So out of all of these, the natural log of concentration versus time gave the best R squared. That is saying that with respect to the A, whatever that substance was, it is first order in A. So if I write a rate law, then it's going to be the rate is equal to K times A to the 1, which whether you show the 1 or not, it means the same thing. So this would be a rate law for this particular reaction with respect to concentration, with respect to substance A. Because we know it is first order. Now, when I obtain the equation Oh, can't read that one. It was negative 0.0231x. Plus 2.3027. Now, if this is, since this is first order with the natural log of A, that means that this equation is equivalent to the natural log of A at a given time is equal to a negative K times T plus the natural log of A of the original concentration. From this, you can see that the rate constant can be determined because a negative 0.0231 is equal to a negative K. So the rate constant is equal to 0.0231, and that is going to be per second because again, this is first order and that is the rate constant in a first order reaction. Now, while I can go back up to the data and prove to you the original concentration, you could also calculate the original concentration because the y-intercept is equal to the natural log of the original concentration. So 2.3027 is equal to the natural log of A naught. We take the exponential of both sides. And when you take the exponential of a natural log, the natural log disappears. And so A naught is equal to e to the 2.3027, or in other words, your A naught comes out to be equal to 10 molar. So I could have gone back and looked at the data, but I want to prove that you can get to it using the calculation. We can ask, what is the half-life? Of A. By the way, something I don't know if I actually explained is, what does half-life mean? When you talk about something's half-life, it means how long before half of the concentration is gone. And that's what we're talking about when we talk about something's half-life. Well, again, because this is first order, through the graph, we know that T1/2 is equal to 0.693 divided by K. So T1/2 is equal to 0.693 divided by 0.0231. Or in other words, T1/2 is equal to 30 seconds. And yes, I could have looked that up at the data too, because it actually had a point where it showed half of it gone. But not all data is going to get to a point where it's showing half of it gone. You're going to have to be prepared to calculate it. We could also ask from all of this data, what concentration of A will remain after 200 seconds. This, folks, when it's asking for will remain, it's asking you to calculate A sub T. So we're going to use our equation up here. The natural log of A sub T is equal to a negative 0.0231. That's our K value, times our T, which was 200 seconds, time plus the 2.3027 from our equation. So our natural log of A at a given time is equal to negative 2.3173. So taking the E of both sides, you get a concentration at a given time of 0.0985 molar. That's how much will be remaining after 200 seconds. Questions?
You're gonna specify which order we're using in the question.
You have to be able to determine that based off of the graph you started.
Okay,
That
so
had-
it's all like one big problem.
This is all one big problem. And it all starts with which graph gave you the best R squared. That's why you have to identify which graph gives you the best R squared, so you know what order it is, so you know what integrated rate law to use. questions?
So the equation gonna be on the graph.
I give you the R squared, so on a test, you'll be given the R squared and the equation, and yes, it'll be on the graph. You just have to, again, start with which one, go for the R squared. That's your graph. Whichever one's closest to one, that's your graph. And then that tells you the next thing, pieces of information. Okay. Here's another one. So I did the same thing I did previously. This one they collected. They had 0.01 molar solution at 0 seconds. After 1,000 seconds, it was down to 0.00625 molar. After 1,800 seconds, it was down to 0.00476 molar, and so on. So we collected the concentration in the time. I then took them, in the next column is the natural log of the concentration, and in the last column is 1 over the concentration. I do that before I even create the graphs, because, I mean, I'm gonna have to create the graphs one way or another, so I might as well have them all ready to go. And then I created the graphs. Concentration versus time, when I add a trend line, gives me a 0.8685 R squared. Natural log of concentration versus time gives me a R squared of 0.9665. And 1 over the concentration versus time gives me a R squared of 0.9999. It's that one because it is closest to 1. So in this particular case, one over A gave the best R squared. So it is second order with respect to A. Therefore, we can write a rate law with respect to A of rate is equal to A squared. Okay. Besides answering those 3 questions over there, let me give you 3 questions, give you a few questions to answer. One, what is the rate constant? Include units. 2. Um, So what is the rate constant include the units? What is the original concentration of A? What is the concentration of A after 2200 seconds? And what is the half-life of A? Okay, let's look at how it's going. With the rate constant, the big thing is taking the integrated rate law, which you're given the equation, and applying it to the equation given on the graph. Y is 1/A at a given time. The rate constant is equal to the 0.0614. The X is the time, and the 99.283 is 1/the original concentration. That is half the battle, is taking your equation and applying it. That's half the battle to these types of problems. Because once you do that, the rate constant is already stated. The only thing that you had to know is what were the units. And for a second order, it's per molar second. The next thing was the original concentration. 99.283 is equal to 1/A0. Therefore, A0 is equal to 1/99.283. So that comes out to be 0.0100, and it has the unit of molar. Concentration is typically I know we talked about other concentration units in the previous chapter, but in general, the concentration unit we're going to focus on is going to be molarity still. After 22 seconds, well, that's where you're going to take this equation and you're going to solve for 1/AT. That's going to be equal to 0.0614 times the 2200 seconds plus 99.283. 1/AT comes out to be 234.363. So AT is 1 divided by 234.363. Or in other words, it comes out to be 0.00427. And again, because we are talking concentration, we're talking molarity. Unless otherwise stated.
So where does the units of rate constant come in at that point? Because we did that by seconds, which would make sense for the previous problem, but so are we not supposed to convert that to milliseconds?
This is still in second, it's not, this is molar second.
Oh,
So
okay,
that's
I
the
saw it as
concentration. No, that's the molar second. Sorry, and I can understand it. No, it's molar times second.
milliseconds. Yeah, that makes sense.
And then the last thing is the half-life. Well, half-life is T1/2 is equal to 1/K times A0, which you've already calculated those. So that's 1/the 0.0614 times the 0.01. So you get your answer of T1/2 at 1,629 seconds. Questions? As I said, I actually show you how to develop the integrated rate laws, the equations, in the flipped classroom. But for the most part, we're going to be utilizing them rather than I mean, I'm not gonna ask you to develop them, I'm gonna ask you to use them and know when to use them and what they mean. That's more important to me than you being able to derive them. I derived them for you. I want you to know when to use it and what to use, what it all means. Questions? I want to just bring up a little bit into the topic simply because I did this morning before I gave out. What we're going to be focused on tomorrow is collision theory. And the part I want to bring up is I want you to think about what it means when I say collision theory. Collision. In order for a reaction, we've been talking about these speeds of reactions. The speed of the reaction, the speed of the reaction. I mean, okay. Well, what's the speed of the reaction based on? Well, in order for a reaction to occur, most of the time, you have to have collisions. Now, let's take this room and assume that we've taken all the desks out of this room. And there are only 2 people in this room. What's the likelihood of those 2 people colliding? Minimal. I mean, I guess if you really are intentional on colliding, that may be, but otherwise, the likelihood of you colliding is very little. But now let's put the entire class, both this group and the other group, in here. What's the likelihood you're going to collide? We've been talking about how concentration affects collisions. You increase the concentration. In most cases, you increase the collisions. And therefore, you increase the speed of the reaction. Now, there is another thing that will increase the speed of reaction. And that is energy. Energetics is what drives chemical reactions in general. It's energy. And let's say that there are 20 people, 10 people in here and you're walking around. The likelihood of you colliding is not going to be that great. But if you're running around and bouncing off the walls like little kids, the likelihood of collisions is going to be much greater because now you have more energy. So there's that factor. There is one more factor. So we got to have collisions. And the more concentration we have, the more likely we are to collide. But also we got to have the right energy. But there is one more thing. We got to collide with correct orientation. And that's what collision theory really focuses on, is all 3 aspects have to come together simultaneously in order for a reaction to occur. What we're going to do tomorrow is we're going to be looking at this collision theory in greater detail, but we're also going to spend more time on, because energy is the driving force, we're going to spend time on energy of activation diagrams and learning to interpret those and what they all mean. And so that is our big task for tomorrow. And with that, I will bid thee adieu unless you have questions for me.
Your office, which tomorrow, like before class.
Yes.